so I have two presentations. They're both, hopefully I can keep them to like 25 minutes each or so. And the first one was solicited. Joe Novosel attends a meeting in Ontario, California. That's kind of amateurs that are doing advanced work that's kind of semi-professional. And so I was fortunate enough to be hired by Lowell Observatory to operate their 42-inch telescope associated with the DART mission. And that's what I'm going to talk about first here. So the first thing I want to make sure happens, where's the share screen thingy? Okay. Thought I knew how to do this. All right, so let's, yeah, I gotta get on and share my screen. I'm screwing it up already. Share screen, share the presentation, and it's that one. So can everybody see the title of the presentation? Okay. And
yeah.
All right, good deal. And now I think if I go full screen here, that should still be good. All right. So as I said, I got hired by Lowell Observatory, and partly because my niche in the hobby, I have a lot of niches in the hobby like everybody, but has become asteroid observing, where I do photometry. You measure the brightness of asteroids, and from that you can figure out what the rotation period of an asteroid is. You can figure out the shape of the asteroid if you do enough of those types of observations and reductions. And so since I kind of knew how to do that, Flagstaff's 2.5 miles or 2.5 hours from my home. I got hired to work up there, partly because they need somebody to babysit a telescope all night. It's not one of these robotic ones on a script, because it's a 1970 telescope. So they need somebody to stay up all night. And not that many people really want to do that, but I like doing that. So just a summary here. The name of the asteroid is Didymos, which is on the left at the bottom there. And it has a binary companion called Dimorphos, and I'll get into that in a little bit. Because Dimorphos in its orbit around Didymos has eclipses and occultations, the light curve, your measurements of the brightness, will show these dropouts in brightness when those things happen. And it's a way that most binary asteroids have been discovered that way. And so they knew already what the period of revolution of Dimorphos around Didymos is, or was, I should say. And so let's smash into it with a spacecraft. And it's going to be real near the Earth when this happens, only 7 million miles away. And they did that about a year ago, minus 1 week. And let's see how much the orbit of Dimorphos around Didymos changes from impacting it with a spacecraft. They hit it head on in the orbit to slow it down so it would go into a more inner orbit, and that was going to change the period of revolution, which is close to 12 hours, and we'll see, is it going to change it by 5 minutes or half an hour or an hour? And when you get that answer, then it's part of planetary defense, as it's called, where you can now see how much could you deflect the killer asteroid that's coming, right for Fort Wayne. So what does it take to do that? So just a little bit background about the asteroid. It was discovered in 1996 at Kitt Peak. At the time, Spacewatch was doing a lot of asteroid discoveries. Now it's being done. Catalina Sky Survey near Tucson, north of Tucson, is actually dominating the field, and we're really faint as far as the ones that can get discovered now. Back in 1996, you could discover a 16th magnitude asteroid, and that's now they're down to 19 or 20. You can see at the bottom is 3 images sandwiched that show the asteroid's track. Those are the discovery images of Didymos. So a binary nature that was found out 7 years later, 2003. Petr Pravic, who's up at the top, is the man for binary asteroids, for everything asteroids. He's an amazing guy in the Czech Republic. But at the time, they estimated that the orbital period was 11.9 hours, so just short of a half a day. And they already knew the rotation period was a little bit over 2 hours. Those are 2 very important numbers as we go through this. Didymos, both of these, the asteroid and its companion, have clever names. Didymus is named for twin. There weren't a lot of binary asteroids known back then, and now there's over 500 that are known. So that was Greek for twin, and Dimorphos just named a few years ago, or just before they knew the DART mission was going to happen, or before it happened, they named that as having two forms. So that means that after they crash into it, it's going to have a crater, it's going to have a completely new form, and it's going to liberate a lot of material, a lot of dust and boulders, that kind of thing, which we'll see in these photos. So here's a NASA slide that shows just what mutual events are. So on the bottom is what we call light curve. You can see as it comes out, you have the combined brightness of both of them, but as it passes in front, that brightness is going to drop. And that's going to happen twice every revolution of the secondary body around the primary. And so by measuring that, you can figure out what's the orbital period of Dimorphos around Didymus. The good news about picking this asteroid was that they knew that it's in a real eccentric orbit, and you can see, hopefully you can see the cursor here, that it goes way out beyond the orbit of Mars and then comes very close to the Earth. So it was only about 7 or 8 million miles away when the impact happened a year ago. And that means that Didymus was nice and bright. And by that, I mean, it was about magnitude 15, which is bright by standards of 1-meter telescopes. And so we were able to monitor the changes in this asteroid as it got impacted by the spacecraft. Hope that this is going to play. Maybe not. Oh, this is not the one. That's a movie. Sorry. So here's kind of a schematic of what was going to happen that was put together a couple of years ago. DART spacecraft shown here, and it's going to impact Dimorphos head on. Dimorphos is going right to left in this figure in its orbit around Didymus. And before that impact happened, not long before, they released a CubeSat called the Licia Cube, that was by the Italians, and that was going to take an image or take multiple images of this impact taking place. So you'd be able to see all these fragments flying off and everything. And that ended up being pretty spectacular. And then it's not going to go into orbit or anything. It's just going to fly by and take whatever images it can as it flew by. That was a very wise decision to have that CubeSat along on the mission. So let's see if this is going to, yeah, looks like it's going to try to play here. This takes a little bit too long, but it's going to show you the original orbital period is 11 hours and 55 minutes. And it was actually known down to fractions of a second. There's no orbital period of an asteroid that's known better. So now they're going to zoom out and show how the spacecraft is going to come in and crash into Dimorphos. There's that Licia cube, and it's going to fly by and take pictures. And even the impactor had a camera on it. Now it's going to be in a new orbit, and I kind of gave away the punchline here, but the new orbit is going to be reduced by about a half an hour or so. Of course, they didn't know that ahead of time. So let's look at a movie, which is sped up about 10 times, that are the view from the camera that's aboard the spacecraft. So obviously on the left, the larger object is Didymus, which was of course never seen before at anything like this resolution. It was just a point source, like a star. And then Dimorphos approaching and approaching. And yeah, I was in the Zoom meeting as we all watched this with jaws, slack jaws, you know. And so here's the last few of the frames until finally the camera goes out when it crashes into the boulders there. So that was quite a thing to watch, and it was as successful of an impact as you could have wanted it to be. As I mentioned, the Licia CubeSat, grossly overexposed, but that's not necessarily a bad thing because you're looking at ejecta, which is all these streams of material. This is all boulders. So even you could see it in the previous slide that both Didymus and Dimorphos, they call them a rubble pile. So it's not like a hard stone or like a giant boulder. It's comprised of thousands or tens of thousands of boulders that are just rubble that is all coalesced. So when you smash into it, these things are going to be released and go flying behind it. And that's actually a big part of how much that orbital period got changed, which I'll get to at the very end of this presentation. As it happened, here's images from September 26th of last year. I let this run a couple times. So this is the Atlas telescope in South Africa. And there's, after the impact, it's moving right to left. It gets impacted from left to right. This is running sort of slow, but I guess it's okay. And so now you're seeing the big plume. I was still in Tempe, which is metropolitan Phoenix, where I can't see the Milky Way. And it's really light polluted, but I observed 200 nights every year for the last 6 years doing this type of work. And what I did is put my 4-inch telescope, my little refractor, on top of my 12.5, which was able to see over the top of the observatory wall barely. I didn't mention that the declination of the pair was negative 33 degrees, so way down near the southern horizon. So what I wanted to do was 2 nights before the impact and then 1 night after the impact. So we'll let this, there's the 25th, the 26th, and the 27th. Always the same exposure on all these images. And you could even see in my tiny little 4-inch refractor that I was able to show that this plume of ejecta, all this stuff that now is increasing the diameter of the asteroid, if you will, with a big cloud of debris, made it brighten by about 2 magnitudes. So it went from 15th magnitude, I think it was more like 1.5 to like 13.5 magnitude. So now we get to the trip up to Lowell Observatory, which for me began on October 1st, right at the end of our monsoon. There's the old familiar forest fire smoke that's plaguing the world these days. This is an image that I took with a drone of Anderson Mesa, which is about only 7 air miles away from Flagstaff. Is that right? I think that's right. And there's the San Francisco peaks, the highest peak in Arizona at 12,600 feet up in the background. And just a quick review of the telescopes. 72-inch telescope was bought by Boston University, and they observe it they use it every clear night, is in that large dome. It's getting on almost 100 years old now and still working. 31-inch was decommissioned a while back. In the foreground, they have just put a 1-meter plane wave in here in the past year. So this is an old shot before they did that, and they've made the dome look a little nicer, and it's going to be a real workhorse. And that's in contrast to a sparkling new 1-meter plane wave is a 1.1 meter or 42-inch Hall telescope, which is the one that I got so intimately familiar with in this dome. It's a wonderful sight, even though it's that close to a city of 70,000, the sky brightness is only 0.4 of a magnitude above when there were no lights on planet Earth. So it's still a very nice dark sight because lighting ordinance in Flagstaff, those are the best in the country, and it really makes a difference. That's a beautiful sight. Here's my drone shot of the 42-inch on an old fork mount. So I said real old scope. One of the most wonderful features is that when you're up on the observing deck, you can walk around this catwalk. So I'm still very much a visual observer at heart. And so when the scope is cruising along and I don't have to babysit it for a half hour or an hour at a time, then I spend a lot of time just looking out at the sky from the catwalk. And it's a nice sky. My star chart of my visits to Lowell when I operated the telescope, each one of these visits were about 2 weeks each, 12 days kind of thing, 12 nights. And at the beginning, my first 12 nights, Didymus is moving real fast because it's close to Earth. And the impact happened back here on the 26th. So you can see these constellations like Lepus and Colombo, which are down in the dirt from where we are, and even worse in Indiana. So it only rose at about 1 in the morning, but we'd get 4 hours observing, 5 hours observing or so before nautical twilight. Then what happened in October was it's higher now. It's near the celestial equator, but you can see it's crossing the Milky Way. And I'll show you a slide of that shows just how many stars are interfering with this type of observing. Every time the asteroid passes in front of a star, that's contaminating our photometry, the measurements we want to do. Then we got into November and December. I spent both Thanksgiving night and New Year's Eve up at the observatory. That part goes with the territory. You want to observe every clear night, and there were a lot of clear nights. So here's what ended up happening was they crashed in with the spacecraft from about left to right. And these little horns here are ejecta plumes. And then a tail, we kept accidentally calling it a comet because it was like a tail pointed away from the sun. Um, since I'm speaking to a Fort Wayne audience, maybe they get the joke on spelling it K-O-M-E-T. I don't know. Yeah. I grew up in Muskegon, Michigan, and I followed an international hockey league team called the Muskegon Mohawks. And I used to love the Fort Wayne Comets jerseys. Like, looks like a circular saw blade on an orange background. It was so cool. So there, anyway, I'm a big hockey fan. So you can see that it was moving really fast. This is, I think, 2-minute exposure, if that. And these stars were tracking on the comet here, and the stars are streaking by in the background. But this tail persisted for months and months until the asteroid was too faint to pick up with even a 4-meter telescope, and eventually went behind the sun. My animation, again, this is taken with the same with the 42-inch telescope, shows it moving across the sky. It gives an idea of what a busy star field will look like when you image deep with a 1-meter telescope. So anytime that it's passing in front of one of these stars, you just have to eliminate those data points because you can't subtract the bright ones successfully. And that's what we were kind of stuck with, but you still got a lot of data, and we had a lot of clear nights. So we actually did far better than I think anybody anticipated, being up north and everything. Okay, so I mentioned the light curve, that animation about 5 or 6 slides back that showed what a mutual event does. But before you get to mutual events, you just have the rotation of the asteroid itself, and think of an asteroid as like a potato rotating. So you'll get 2 maxima and 2 minima every time it rotates, and that's every 2¼ hours you would get these minima, which should match up. If there was no mutual events, if there was no eclipses or occultations, these should line up perfectly every 2½ hours. And you can see that they're not. What's happening are these mutual events, which are happening every 11.9 hours, are kind of corrupting the light curve and making it very convoluted. So there's a lot of nice Fourier analysis kind of math that goes into this, where you can then isolate the mutual events. And that's the whole key to finding out what an orbital period is. And I'll spend minimum time explaining this, but if you didn't have mutual events, this is a model of just rotation. But since those happen, they cause these dropouts, that these reductions in the brightness. And all we're seeing is on the y-axis, we're just seeing what's the magnitude of the pair of Dynamis and Dimorphos combined. So then you actually isolate, you subtract the data points from the model, and you get what are called residuals. And now you're able to isolate these events. And what was great about this is that you started with 11.9 hours before the DART impact. And it was obvious even within 2 or 3 nights after the impact, with this big cloud of kind of contaminating debris. We didn't know how that would work out. Pretty quickly, we were able to figure out about how much the orbital period was changed. So it changed to 11.372 hours from 11.9 whatever hours. And NASA had the administrator had to do a press release, and was able to do that within a week, was able to say we've reduced the orbital period by a ½ hour with this successful mission. And what does that all mean? And even today, I'm on the email lists that there are people who are working all their time, full time, probably 20 or 30 scientists on every possible discipline you could imagine, analyzing the data. And there's still questions. It's not just the orbital period, but a lot of other disciplines. I'm just focusing on the small thing that I know. So what happened was this impact, as I mentioned early, happened at a real southerly declination. So if we look at these telescopes, that's the Swope on Las Campanas in Chile, another Chilean telescope, the Danish telescope, yet again in Chile. There's one in South Africa in Cape Town. And then one of these doesn't look like the other. Up at latitude 33 degrees north of the equator is Lowell Observatory. And you can see we did pretty well, that we're lining up with the data real well. And then they do the same thing called the decomposition to show when these eclipses happen. And we were able to actually contribute way up at our northerly latitude. And that was the really exciting part. And then further on, as you got into November and December, there was a lot more work to be done with observing. So every clear night we observed it. And this is probably the hardest one to understand. I'll just mention that you would observe 11 hours 55 minutes before the impact, and now it's 23 minutes, 11 hours 23 minutes. So we got that information within a week of the DART impact, and we could find that out by doing this mutual event analysis. What they expected, if you had a solid rock and it wasn't a rubble pile, it wasn't a bunch of boulders that kind of eject the big plume, they call this a beta factor. So if you just hit this rock with the spacecraft, that's real easy physics. What should have happened had it been a solid body is it would have reduced the orbital period by 7 minutes. But what actually happens is you hit this thing face on, and now all this debris goes spraying out in that direction. And it is what I like to call a thrust reverser. I spent my whole career in aircraft engines, and so I could relate to a thrust reverser where you land the airplane and now you change the direction of thrust and it becomes a brake. And that's what happened here, was that there was so much debris that came off quite a bit that you ended up reducing that orbital period by 33 minutes instead of 7 minutes. And that was just kind of a cool thing. So all of this came together beautifully for us at Lowell Observatory. And I'll just point out a couple names. Christina Thomas is the lead author. She's at Northern Arizona University, which is in Flagstaff. My hiring manager, Nick Moskovitz, is the man at Lowell for asteroids. My mentor for the last 30 some years has been Brian Skiff, who's worked at the observatory forever and since the late 70s. And then my name, and this went into Nature, which was a prestigious journal to get published in. So Nature, pretty early after the impact, in early March, only 5 months or so, ran 4 papers that had to do with the DART impact, and Lowell Observatory astronomers were on one of them. And that was pretty exciting. That was one of the big rewards of it. And now there are further, much more detailed papers than these preliminary kind of press release style papers that are still in publication today. Finally, my manager, Nick Moskovitz, has a 3D printer in his house, and he appreciated the work that he did. So he made 500:1 scale models of Didymus and Dimorphos, which are on my desk as we speak right now. And these are everything that are accurate, that what we know about the surface of the two. That's Clyde Tombaugh, discoverer of Pluto, in the back. And so really a rewarding project, and hopefully in the next year or so, there will be some sort of funding, probably nothing this exciting, that I'll get to work part-time at Lowell Observatory again. So that is talk number 1. I don't know if you guys, and I hope not to run too long. I think I got that in within about 25 minutes, which was my goal. So I don't know if you guys ask questions or anything, or if you want me to go on to the next talk.
You don't want to stop for questions?
Yeah,
Just
okay.
just
We'll stop for a few questions.
Yeah, you'll have to say, yeah, make sure they're on a microphone that I can hear it. Okay.
Where's our microphone, Jim?
It's buried in the
On
can.
the tripod, I think.
Yeah.
Right. I'll get close. Hi, Tom. Joe Novacell.
Oh, hi, Joe.
So why didn't observatories like University of Texas or what is it in Arizona on Graham Mountain or something? There's some observatories. was it scheduling, or why didn't they want to get involved at all? They're further south, so it would seem like a
Some, some of them did. Yes, it's scheduling because a lot of that is 4-meter telescopes. They're very large telescope. There's one on Magdalena Ridge in New Mexico. I think it's a 3.5 meter. And most of the involved telescopes, though, were more in the small, if you will, 1 meter to 2-meter kind of range. When you get up to the large binocular telescope, 2 8-meter telescopes on Mount Graham, and you get to these, even the large Chilean telescopes, these 8-meter, 6-meter telescopes, they are a lot less likely because the scheduling was for more, I guess, esoteric projects. But one telescope that did get involved a lot that I forgot to mention at all is Lowell's flagship scope is the 4.3-meter Lowell Discovery Telescope. And that's down the road from Anderson Mesa, another 30 miles or so, another half hour down the road is a 4-meter telescope. And that actually did get used, not for the initial impact, but in the later November, December, and even after I was gone earlier this year. So those did get used, but it's usually the usual answer is scheduling and the fact that you had to, in my case, or in our case, in any of these cases, to do these light curves, you have to stare at one target for hours and hours for the better part of a night. And that's not how real large aperture imaging generally works. You get a half a night or something and you point at multiple targets. So a dedicated scope being able to do this was really valuable.
That's enough. Thanks, Tom.
All right.
Hello, I got a question. So it slowed down when you hit it. Will it
Yep.
speed up again? Or
No.
will the orbit change, or will it decay, or is it static? Just
It won't speed up, that's for certain. And that it really is almost completely just that impact and the plume of debris. But there was some slowing down after the initial impact. So it wasn't completely answered in the first week or so. But that's even done now that we're down to just the finest particles of debris that are being sprayed off of it. So all the large boulders go first and then smaller and smaller particles. So it definitely won't return to normal. And I didn't mention the HERA mission, I think it's HERA, that is just launched, I think, and it'll be there, I think, in 2026, is going to go to this same asteroid and observe, here's what we did to it. And that's going to be a great mission. So that's a few years away. But as far as that orbital period, they got the answer they wanted. The answer I wanted was, did you deflect it with this enough, with this impactor enough, so that if it was coming straight for the center of the Earth, would you have been able to deflect it enough? And the answer was that with this one and something the size of Dimorphos headed for the Earth, you would have had to have had 40 years of notice and then hit it 40 years before it came to the Earth. So not nearly enough mass and not nearly enough notice, because we don't discover them that and know their orbit that far in advance. So that's where the Vera Rubin telescope is going to go a lot deeper in surveying, and we're going to know more and more about asteroids that can possibly impact the Earth. But at this point, you would need quite a bit more mass for something even as small as Dimorphos coming toward the Earth.
I got a quick question. So about missing, it would still collide with the Earth. That's really interesting. I guess some of it would depend on where it was hit. I guess you guys were very happy that you hit it just to begin with, that you were able to strike it, let alone trying to hit it on a side or a corner, which would cause more possible deflection.
Right.
Is that in the realm of possibility, or is that?
Yeah, I think the real, well, maybe I'm not seeing the geometry that clearly, but you would have to strike the asteroid from the side, right? You'd like to hit it 90 degrees from the direction as it's coming toward the Earth. And so that seems like an additional challenge. How do you set something into that trajectory? In this case, it was pretty straightforward to hit the center of Dimorphos as it's coming straight toward you. Yeah.
Well, yeah, I mean, you hit it in the center, but if you had hit it more to the side,
Yes.
would that have improved the odds rather than 40 years? Maybe.
Oh, no, I think that's best case scenario, hitting it, I guess, from the side more than you hit it in the side. So where you hit it off center, you obviously you always want to hit it perfectly on center. And I think you want to hit it from 90 degrees from the direction that it's heading toward you. And that was figured out as how much did we change the velocity? So it wasn't too hard of a math problem to say, now the radius of the Earth is about 4,000 miles. We're trying to deflect it by 4,000 miles. And it's just, I know the velocity and the distance, how much time do we need? And yeah, that's how that was figured out.
And I guess you learn a little bit about the density of the asteroid.
Oh boy, yeah, you learn a lot about it. It's all way over my head. Other than the orbital stuff, how much doing the light curve decomposition, the stuff I've talked about here is one. I mean, it's the main reason that it was done, that the program was done, but the amount of work on ejecta and cratering and everything is just amazing how much is still active, and so how valuable the mission was, just to all the side benefits that we learned from it.
The 40-year number that you stated, that's an eye opener. That
Well,
shows us that we better get our act together.
Well, and it's not, so there are very good asteroid researchers who think all of this is kind of a, frivolous, and I don't completely disagree with that the chances of getting hit by something of that size when we've surveyed as deep as we have by now, especially after the Vera Rubin telescope surveys everything multiple times, that we probably don't have much danger of this happening in the next 1,000 years. So but there's always a chance. So yeah, that's why you do it. And it's fun. So it's fun for astronomers. It gives us funding and lets me go up to observe with a 42-inch telescope. So I can't object to it.
Tom, you might want to go on to part 2 now.
Yeah, I'm getting behind here. So let's go to that one then. This is going to be a very different presentation. Nothing about Lowell Observatory in this. Okay, so now I'm going to talk about doing time-lapse imaging, which is one of my fortes, one of my favorite things to do ever since I got started in the hobby and started learning how to do it. And this is going to be a little different time-lapse imaging because it's not going to be during the course of a night, and it's going to be decades and centuries, and trying to watch objects move. Everybody's seen great images, time-lapse images of Jupiter rotating, Mars rotating, lighting changing on the moon. This is not going to be that, even though I love that stuff too. And so we'll get into it. So here on the Earth, just in a few decades, as I'm showing here, this is pretty depressing. I live here in Tempe, just south of downtown Tempe.
Hey, Tom,
Yes.
you didn't advance the slide.
We're still looking at the dark presentation.
Oh, all right. Let me, I have to share a different one. Sorry about all that. Yeah,
Okay.
it's
I
like,
just didn't
yeah,
want you to get too far and have to make you go back.
yeah, thanks. So, all right, screen sharing. Share. So do I stop the share and then start a new one? I think that's the best one.
Yeah, usually you got to do that. Yeah.
All right, doing that. And now I'm going to share this presentation, which is here. Yeah, thanks for that.
Great presentation so far.
Oh,
Tom.
thank you. Yep, so far so good. All right. So now we can see the title slide for a century in the
Yeah.
blink.
Yeah,
Great.
you're good.
Okay. Thanks. All right. So I live here, and Tempe, right in the middle of everything. 4.5 million people in metropolitan Phoenix now. And since I moved there in 1985, close enough, you can see how much growth has taken place. It was about half this population when I moved there. So just an example of what we're going to be looking at with this presentation. So when we, get rid of that title now. There it goes. Okay. So when we look at just a pair of images side by side, those just seem like everything's kind of fixed when we look at deep sky objects in space. But they're not really. So here's the first one of these, and this is not my image. This is two Hubble Space Telescope images that I put together from about 20 years apart. Changes are pretty subtle. They're going to be subtle in all of these, but that's real change in the pillars of creation in the Eagle Nebula. So this is the kind of stuff we'll be looking for in this presentation, only using my images as the current one and going way back for the old stuff. So which ones are going to show motion? And obviously the closer they are to us, the more angular change they're going to make for a certain velocity. And you want objects with that are moving fast, obviously. And that includes clusters, supernova remnants, and especially planetary nebulae, which are the highlight. So if I can get something from 100 years ago, put it together with today's image, you might be able to see some motion. And I can do all of that without doing any kind of spectroscopy at all. It's actually motion transverse on to our line of sight. So the best sources I found were from way back, just Googling and Googling until I find old stuff from archive images and books from turn of the century, 1911, even especially the Palomar Sky surveys 1 and 2 in the 50s and 90s were great for the reference images. So archive and current images. So we start with the archive images. There's a Lick Observatory publication, which is a nice picture book from way back in 1908, and they give the year that the images were taken. The 36-inch Crossley reflector at Lick Observatory, and I included this just to show how difficult it was for imaging back in the day. So what they would do is during the exposure, they would have an assistant and the observer, and they would have to manually guide these multiple hour exposures. So then they would just quickly change places every half hour. So then you could get a couple exposures for 4 hours each during the course of a night. And you realize how easy we have it these days where we have auto guiding. There's the 60-inch reflector getting taken up the mountain at Mount Wilson, great historic telescope, and I used quite a few images from it as well. Palomar Sky surveys on the left is actually Edwin Hubble at the 48-inch Schmidt camera, the Schmidt telescope. And I always want to be smoking a pipe when I observe. And so there he is. And here's a great site, the digitized sky survey plate finder, which you type in an object name or its coordinates, and you can go get red plates or blue plates, whatever the wavelengths they shot in, from the POS 1 and the POS 2 in the 50s, and then in the 90s again. They use that. Now, of course, they don't have film or plates, and the 48-inch is called the Zwicky Transit Facility, and it has a CCD detector, which is far superior. All right, there's my observatory in the backyard without the 4-inch refractor on it. That's the 12.5-inch from AG Optical. It's a perfect telescope, f6.7, and you pay for that, of course. The mount is a 10 micron GM2000, and the camera is a SESBIG ST6303. 6303 is a camera that does not have anti-blooming gate, so you get big blooms on star images, but it's better for making measurements for doing photometry than one with a blooming gate. So I get a field of view of 3/4 of a degree by a 1/2 a degree. And then I have one of the filters, most of them are just the photometric UBVRI filters, but I also have a 7-nanometer hydrogen alpha filter in one of the slots. And that came in really handy because of the light pollution at my site where I'm losing 3 magnitudes. So making the image pairs goes like this. I just drew these lines in actually today, hopefully it helps, is I get, that's called Command Module Observatory. That's my observatory. And here's something from the Palomar Sky Survey from 1994, whatever it is. And I see that asterism is the same. Now I have to align them. And so this pair is, if you just scale them to make them the same, you'll get this. But that's unacceptable. Everything's shifting around. So if we scale and rotate it, It's getting better, but it's still unacceptable. The stars are jumping around, that's distracting. So then there's software that will align images, a reference image to another image that'll warp the frame so that all the stars match up. That's what we want right there. So that's POS versus my backyard observatory, and that's what we're looking for. When you take an image, say, from the Hubble Space Telescope and compare it to another image, say, from back in the 1950s, it's real distracting when you have colors and details are different between them. So what I do is I call this lowest common denominator imaging, where I'll take the worst of the two images of the pair, and then I'll blur the Hubble Space Telescope image and make it monochrome and make it look as much as I can like the HST image. And that way you get to see a high proper motion star without all that distracting color. So almost everything I'm going to show here is just going to be in black and white. So you can see the power of being able to do this is that now you're able to see things changing in the sky, which is a big part of why I'm in astronomy. Is I love watching these changes, whether they happen over the course of hours or a night or decades or centuries. So I use a site which I like a lot called easygif.com, and really nice, perfect interface for making these comparisons. And it even allows you to crossfade between frames. So Photoshop is one way of doing this, and I love Photoshop, but its animation couldn't be much worse than it is. I think they get the flunkies that work in the basement of Adobe to do the animation thing, and then they never improve it over the years. It's just unbelievably bad and unintuitive, but it does work. But this site is so much better. All right, so there's Michael Jackson morphing over the course of 40 years. So sorry I had to do that to you. So, all right. Okay, so here's how to view the slides, because this really takes, if you're going to have to really look right into the screen like this to see these changes. And I'll kind of give you the guide here. So I'll always have a counter in the corner here that's going to show 55 years of elapsed between the two. Now I'll usually put a scale bar. That's ideal to do that. You should always image with north up and east to the left. I have to get that in every talk I ever do. It shouldn't be any other orientation. Makes everything easier for everybody. And then in this case, there's some moving stars. They're sliding back and forth. And I put the rectangles that are oriented like the vectors of motion. So, and ignore these artifacts. So there's always going to be hot pixels or just noise, thermal noise that I didn't get out successfully with a dark frame. And that's the stuff not to look at. Now that I've drawn your attention to it, don't look at it. All right, so moving stars. Back when I was getting started, like in the late 70s, I got Burnham's Celestial Handbook, as many of us did, from the Astronomy Book Club for $1 for all 3 volumes. And sadly, Robert Burnham didn't make any money for that reason, and had a tragic story. But this was one of my figures that I started looking back in like early 80s. And here's this V-shaped asterism at Barnard star, which has the highest proper motion of any star in the sky, 9 arc seconds per year, or quarter of a degree, half the diameter of the full moon during a typical human life. So I wanted to visually view it. And then when I got the capability to image, here's the first of these slides. So we look at Palomar Sky Survey 1 from back in 1950, and we see this huge motion. Of course, they show a lot more stars because they're observing with a 48-inch in a dark site, but there's everything registered, and we're watching this star move across the sky. I'm not showing it here, but every year for the past 7 years, I've been making a GIF that just shows its motion year to year. This is just comparing it over a longer period of time. Pleiades are nearby star cluster, and these, how do you know if it's a Pleiad or if it's a foreground star? Well, they've measured the proper motion to real good precision now, and that goes into software. My favorite thing on my phone is Sky Safari. So I'm going to run a simulation from Sky Safari for 30,000 years. That's going to show all the Pleiades moving. And obviously that's not one of the Pleiades stars. That's not one moving across the field. Well, we can see the Pleiades moving. So if I can do that, I should be able to do that over a shorter period than 30,000 years. So here's what it was like 30,000 years ago when they invented the telescope, but they didn't have optics yet. So I used Paul Lynn's image. He's a friend here in Phoenix, and then a Lick Observatory image from 1899. So a real huge baseline that I went back to 118 years. And you're probably not seeing them yet, but now that I do this, hopefully this helps. All these stars that have white rectangles around them are moving with the same vector. Those are Pleiades stars. See, every one of these are sliding back and forth. The main ones that we see naked eye are just too overexposed or too saturated to be able to see their motion. But you can see here's the non-Pleiades stars. Those are not members of the star cluster, just happen to be interlopers that are in the frame. So you really see how a star cluster isn't just a group of stars that's together. They also share the same age typically and the same motion across the sky. So they're moving across our line of sight while they seem static to us during our lives at over 200,000 miles per hour, which is a theme of this. Most things are moving in the tens to hundreds of thousands of miles per hour in this presentation. Nova and supernova remnants. So one of them is called Nova Persei, and it has created the Fireworks Nebula. And so I'm using some textbook illustrations and then mine, which flashes by way too fast at the end. Then you're seeing this expanding debris cloud or expanding shell around it. The very last image here, it's a reflection nebula, so I can't go through the right filters and I have to go in light pollution, and it's that one. Just barely shows up, but it does show up one more time through the sequence. And that's enough right there. The Veil Nebula is after this because it's a little more obvious. So I did the supernova remnant that's up in Gemini, north of Orion, IC 443, using my H alpha filter, and then an image from the Palomar Sky Survey 1 back in the 50s. Let's zoom in on that a little bit, and maybe you'll be able to see the motions. Just a gentle rocking back and forth in that direction. So you kind of take these filaments here, and maybe you can see them, and maybe this helps to put a little grid over the top of it, and then you compare it to that grid. So this is one of the most subtle slides that I'll show, or image pairs, and they'll get easier to look at mostly after this. The supernova remnant that we're all familiar with is the Veil Nebula. It's spectacular visually, and of course everybody's imaging it better and better these days. Supernova had to have been here, and then you have these expanding clouds, including Pickering's wedge, that are going out that way. So I wanted to be able to show 6960 going to the right, to the west, and 6992 going to the east with an image pair. And that's what we have here. So you have to look at this closely, and you'll see that on the left, it's just floating back and forth, left and right. The counter's down here. There's 2018 and 1953. Same thing's happening on this one, but it's moving in the opposite direction. That's 6960, moving left to right over that period of time. So what I did was zoomed in on 6992 and registered on the nebula instead of the stars. So now the stars are going to kind of go back and forth. And what I'm seeing is a kind of three-dimensional twisting of the nebula, where it's kind of turning back and forth around an axis that runs up and down the screen. Now it's kind of a surprising thing. Always in these image pairs, you'll see high proper motion stars. That's because we're going over a century. Pickering's wedge, what I found out here, I kind of expected all the motion to be in one direction, but it's more chaotic. So I made arrows that show that some of these shock fronts are moving in the opposite direction as the main part of the nebula is. So this one, yeah, I'll say this is the hardest one to look at now. All right, here's an easy one to view, where I'm just going to take two images. I have a version of this that uses more, but just to show a striking difference between the Crab Nebula now and the Crab Nebula back at the turn of the century. And you can see the expansion of these filaments is huge. So maybe we get a supernova in our lifetime and we can see something like this. And it's not in the southern hemisphere like the Large Magellanic Cloud supernova. So emission nebulae are sort of difficult. I thought I took this one out. I'm going to go by this one. This is probably the hardest one to see the motions in. So let's go to the Trifid Nebula. And these are pretty easy to see. So emission nebulae are not expanding clouds. There are kind of random motions. As you can see from the red arrows are pointing to features that are inside of the nebula that are changing in very different directions. So I see this shape, this kind of inverted V, and I thought it would be expanding in the opposite direction, but it's not. It's just a shape. It's not doing that. Similar to what's near the bottom of the frame. The yellow arrows are just pointing to high proper motion stars. The Pac-Man, kind of difficult to see, but I put a grid up for this one. And the things to focus on are not in that area, rather they're in these kind of these fronts, these shot fronts that you see here. So right along that line, you're seeing differences in the structure of the nebula. And this is only over a period of 29 years from the Palomar Sky Survey 2. Now we get into the fun stuff, the planetary nebulae. Of course, the most nearby bright planetary is the Helix Nebula, and it's showing real big changes in structure. Here you do expect it to be an expanding shell around the central star. In this case, what I did was I registered the two frames on the central star right here. And what you're seeing is all the stars in the background or foreground are just shifting back and forth because the helix, they're all in the background, I should say. The helix is way in the foreground and it has its own proper motion across our line of sight. So by registering on the Helix Nebula, what you're seeing is these stars rock back and forth, left to right in the background. That was another surprising result to see that the proper motion was as high as this, that you could see it over 100 years of the helix itself, but it's a very nearby object. Dumbbell Nebula, there's nothing subtle about this one either. So you can see big changes in the dumbbell, another pretty nearby object. Now we get into a little bit smaller planetaries. This is NGC 246, which is pretty low for us and even lower for you guys, down in Cetus. And this one is showing the rim expanding. And you get another high proper motion star there and there. Up in Cygnus is another very nice planetary. Some of the changes we're seeing here are because I just couldn't exactly match up the exposures between the two, or the levels, the contrast and brightness. But there are definite changes in 7008. And if you ever image or visually observe this nebula, you know, it's straight up in Cygnus, look for this object, which is a Perit-Kohoutek planetary nebula. So everything else in here is a star. That thing right there, it's not changing between the frames discernibly. That's a planetary nebula that's way off in the background. That we're looking through one planetary and seeing another planetary that's off in the background, which is a lot of fun. Everybody looks at the Ring Nebula. Here are the changes in it during the course of about 100 years. And the Owl Nebula. Owl is a lot more subtle because it's a faint object and it's not emitting as much as I wish it was in the hydrogen alpha, so hard to image for my backyard. And now we're getting more and more obscure. This planetary, it's up in Lynx, I think it is, yeah, near Cygnus, so in the summer sky, which is just leaving us these days. Jones Emberson 1 is huge, and it actually shows up nicely if you have an oxygen 3 filter, if you observe visually, if anybody still does that, and it images pretty well and shows some kind of subtle changes over the course of a century, or in this case 60 years, 70 years. So we're getting near the end of the planetaries. The blue snowball is an Andromeda, spectacularly bright, but small. Well, kind of look at this inner ring and we can see that they're all expanding. And I put a scale bar, you can see an arc minute is that. So you need 300 or 400 power, you need real good image scale if you're imaging to be able to pull out any detail with the Saturn Nebula. What? This shows up. Oh, sorry, this is the Saturn Nebula. So big changes in structure. And again, I'll overlay a grid, probably unnecessary in this case, where you can see large changes. So I just got a lot of fun. And in addition to all the other time-lapse work that I've done, this became a really fun little side project to see, how much is the universe changing? You can't do any of this for galaxies because they're orders of magnitude farther away than everything I've shown here. But you can definitely do it for all the stuff that's in our own galaxy that's not too far away. So finally, get into a little math problem here. How fast is this stuff expanding in planetary nebulae versus what's in the literature? So what's in the literature is all going to be based on spectroscopy. So measuring red shifts or blue shifts as things are coming toward us or away from us. So a blue shift in the case of planetary, we're expanding in the direction of the Earth. But I'm going to show 90 degrees away from that red shift or blue shift. I'm showing this little rim of the dumbbell changing by 5 arc seconds or so, by quite a bit over 120 years. And that's definite motion. So if I can do that for these planetaries, I can lay out a little math problem and say, how much did the edge of the planetary deflect in pixels? I know my image scale in arc seconds per pixel, so I can find out how much did it change in arc seconds. If I know the distance out to the object and do some trigonometry, figure out how much it's changed in kilometers, and then change, just subtract the number of years, change it to seconds, and you will get the velocity in kilometers per second. And that's what I wanted to do with this. And so there's one thing I know better than Photoshop, it's spreadsheets. So here's where you get to see the result of my spreadsheet. So I have a list of planetary nebulae, almost all of which I just showed right there. The known distances, and of course, some of those distances aren't perfect. And that's why you see 2 significant figures, 1 significant figure. They're not out to decimal points or anything. And then all my math, simple math, that went into finding out from my result of what I just showed in the last slide, here's what I get for the velocity in kilometers per second. And here's what spectroscopists got for the velocity. And here's how far off I am. So I nailed it on the dumbbell nebula. I'm getting something almost identical to the spectral result, the spectroscopy result. But then when you go to some of these farther away ones, or even ones with less, with just poor resolution, I'm off by like a factor of 3. But I'm not off by a factor of 10 or anything. So it's a real result. So that ended up being a really cool thing to finish up with. I tried a few other objects, like some stars and nova remnants and even supernova remnants, and they're quite a bit farther away. In this case, I didn't have a way to compare my results. But at the bottom, what I'm showing is that you have velocities that are on the order of hundreds of thousands of miles per hour. And yet, as we look at them visually or even on our images through our lifetimes, we don't see changes. So if that doesn't give you a good feel for the distance out to the most nearby astronomical objects, then I can't help you. What does? It's amazing. So I have one more slide in this, and it's a time lapse that I hope impresses you. And this is a time lapse of something on the Earth, and this is the construction of your observatory over 12 years using images from a site that shows historic aerial images. So you guys are probably familiar with this intimately. I just heard a discussion about mowing the lawn or something. So there's the Fort Wayne Astronomical Observatory in 12 years. And it looks like I got through all of this in an hour. So I hope that was good enough for you. Thanks a lot for listening to my talks. So I don't know, this is less likely to bring about questions, but if you have any questions or anything, Now's the time. I'm going to stop the share.
Excellent work. A lot of work went into that.
Yeah, yeah. Labor of love. Yeah, it's a lot of fun. I mean, about 7 or 8 years ago, I guess it's 7 years ago. My friend Michael Collins, I don't know how to build anything. I know how to do stuff like this and analysis and engineering, but I don't know how to construct a thing. And he's a Renaissance man. So he did probably 3/4 of the work in building my backyard observatory, which coincided with my retirement. And so it worked out terrifically. But the name Command Module Observatory is because his name happens to be Michael Collins. And so, yeah, I'm very happy to have that in the backyard, and it will operate tonight looking at asteroids. It's wonderfully clear here again. We're past our monsoon, and this is the clearest time of year other than June. And I use it every night. And when I'm not observing asteroids, then I do this kind of stuff with it. And it's a lot of fun. Great hobby we have.
Thanks a lot, Tom.
All right, thanks, you guys.
Enjoy the program. Thank you.
All right.
Tom, we also typically, you're out in Arizona, but if you're interested, we typically give a little gift of a set of coasters, Fort Wayne Astronomical Society coasters. If you'd like,
That
You-
actually,
Julie, or send your address in the chat.
I will. I actually
to,
I was gonna say if it's an honorarium, just give it
Yeah.
to International Dark Sky Association or something. I'd rather just not accept those, but that actually is cool. That's, so that would be great. Yeah,
Yeah,
I'll send my address.
there's like, yeah, okay, yeah, there's like a star on the bottom and on the
All
side.
right, yeah.
Yeah, okay,
So Fort Wayne Comet.
Or
yeah.
yeah, Comet jersey. That's what I really want.
My jersey's in my closet. You can't have that though.
Okay. Yeah, I still play. I play twice a week at age 62. And yeah, you wouldn't want anything to do with my stinky jerseys. So, all righty, I'm going to drop off now. Tthanks for having me.
Thank you.